Alright, time for another draftphysics.com, debatephysics.com, also video presentation. So, units, physics, and the fact that they're just made a total mess out of this concept of energy. So again, I will defend the position of Descartes, which is basically to say there's a certain amount of motion in the universe. It doesn't matter whether it's little things moving, big things moving, or forces moving the speed of light, that there's a certain amount of this motion in the universe, and it's always conserved. That is, it never stops moving. So if something's jiggling and it stops jiggling, it means something else is jiggling, something else is moving somewhere else. The energy has migrated, it has been transferred from one object to another, and that's the principle that governs the universe. And physics is implying, they won't say it, but they're implying something else is true. They say everything's conserved, and yet clearly all of these things can't be conserved because of the fact that they have squared the velocity in the kinetic energy formula. That is overtly saying I'm going to keep changing the standards, I'm going to keep changing the units. So I had a bit of a conversation. The subject was brought up, and then I opined to clarify a position that units, that these are all units of pressure. It's all you're saying is how much pressure is something going to apply, how much force, how much weight, and that really is all there is in the universe, is that concept of an amount of weight. And you can have a weight for a constant weight created by gravity, or you can have something that has a net velocity, and that's it. It just has a velocity, and you can take all of its energy, and there's no extra force that will refuel it, so it's a net equation. And physics hasn't even resolved what it's measuring, whether it's an impulse pressure or whether it's a constant pressure, which are very different things actually, in the sense that one is a exhaustible fuel and one is not. So it just makes a terrible mess. So I'll play this clip from Feynman as context. Other physicists have said this, that this is a real flaw in physics, that they can't come up with a better SI system of units that unifies this concept of the energy that's being exchanged. And the energy shouldn't be changing into some other form, because frankly it's conserved as a quantity. If you change the units, then you're not conserving the quantity. Alright, so we'll play this little clip.
For people who like to, if physicists always feel so superior and smart and so on, that people would just like to get them once on something. And so I'll give you something to get them on. They should be utterly ashamed of themselves, because they take the same thing, energy, and they measure it in a host of different ways with different names. Absolutely absurd. Energy can be measured in calories, in ergs, in electron volts, in foot-pounds, in BTU, in horsepower hours, in kilowatt hours, all exactly the same thing. It's like having money, in dollars and in pounds and so on. But unlike the economic situation where the ratio can change, these dopey things are an absolutely guaranteed proportion. If anything could be analogous to it at all, the only hope would be to say that there are 20 shillings to a pound, and that you have shillings and pounds, with one complication that the physicist allows, and that instead of saying he has 20 shillings to a pound, he says he has irrational ratios like 1.6183178 shillings to a pound. So, in addition to that, you'd think that the more modern, high-class theoretical physicists would at least use a common unit, but you can find papers with degrees Kelvin for measuring energy, megacycles, inverse Fermis is the latest invention. We don't need any more inventions. We should all measure the energy in exactly the same. We should measure the energy in one unit and let it be done, instead of having all these different names. And it just shows that people are often also, they want to say, see, I should bring my little boy to show on the screen so that the audience will understand.
Oh, yeah, he's going to do some personal crap. Anyway, that hey, all physicists are human. They're just so superhuman that we can't even relate to them and recognize them to be just shit talkers. Anyway, it's just they're just so full of themselves. All right, so I guess I will find another clip where he basically says energy doesn't come in units, which is just too bizarre. Again, just re-argue. So I'm arguing for the analogy he used, that it's currency. And it's not about the currency being in something else, like a euro and a dollar. It's about nickels, dimes, pennies. And this is the conversion problem. Something can't adjust to you when it's all holding a bank that, it's got a nickel slot. You can't put quarters into the nickel slot, that kind of thing. So energy can only be transferred if it's in the same form. That's why in the Newton's cradle, one object with the same mass can transfer all of its momentum, all of its kinetic energy, if you want to use that silly term, without interruption. It's because the ratio of its energy is in the same denomination, and so there's no conversion necessary. But if you change the mass, then the energy's in different smaller units per electron, and now when the electrons are communicating with each other, they're not going to be going, here, I'll just give you what I have, because what he has is 10 cents and he needs 15 cents. Each electron has a different amount of energy, therefore it's going to push a different amount, and all of that has to be converted, and it can't convert up. Something with 10 velocity can't give something 15 velocity. It can only push it with the 10. So this is where objects then won't be able to completely transfer their energy. They'll only be able to partially transfer it. And that is seen in a ton of experiments where you transfer momentum from a bowling ball, for example, to bowling pins. The pins can't fly off at their maximum speed of collecting all of the ball's momentum. They can only collect a portion of it, depending on the elasticity of the substances you're hitting, how springy they are. It can't really increase the velocity. It can only take what the ball has to give in the form the ball has to give it. Alright, that's okay-ish. So I'll go find the other clip. Alright, should be back.
Now there are other, so we have here the energy, which we could put in our list. And it's conserved perfectly as far as we know, but it does not come in units. And now the question is it the source of a field? And the answer is yes. Einstein understood gravitation as being generated by energy. Energy and mass are equivalent, and Newton's...
So anyway, the unit part is the only one I found bizarrely interesting. Why he would say energy doesn't come in units, clumps, as he's sort of famous for saying. So, did that just happen? Yeah, that was interesting. I think that was interesting. Was it interesting? I don't know. Let me pause and see what the hell that was about. Alright, continuing on with the analysis. So if you use the equations for momentum, just mv equals Newton seconds, some sort of weird denomination, I'm just going to call it momentums. It's a number, and then you get a number for the kinetic energy equation that's supposed to be in joules, and it's just a number. Alright, and the simple truth is that you can do these experiments. Now we're talking about just a mass and a velocity. No force pushing. It's just a mass moving with a velocity. And we're going to say it hits a spring or it hits some other object, and what's it going to transfer is the obvious argument. Is what is the nature of its capacity to cause an effect. Alright, so obviously there's a problem here. Like Houston, we have a problem. Because if you look at the numbers, if you're going one velocity, and that's just a meter per second, it's an arbitrary velocity. We're just, picking one. The momentum number ends up being bigger than the joule number. which, is a problem. Interruptions. Anyway, so, a momentum is greater than the number of joules, which is, rare. Okay, let's just say. And then, if you go with one mass going 2v, then all of a sudden the two numbers match, So, yes, the momentum number is perfectly consistent with the joule number, and you'd say, well, then, 2 momentums equals 2 joules. That means 1 momentum equals 1 joule. So you're saying the two quantities are equal. And if you do this third test with a 3 velocity, all of a sudden now it's more joules than it is momentums. Okay, so obviously this can't be formalized into any conversion. And it doesn't make much sense though, because all these objects are going to have an effect on something. So if it was just an object flying through space and I was just going to smash it into a spring, which one of these numbers is the number that's going to be proportional to the spring's contraction? Now, Hooke's law says the momentum numbers are right. Okay, 3 times the velocity, 3 times the spring compression, twice the velocity, twice the spring compression. And physics says that, twice the spring compression is somehow 4 times the energy. But it can't be 4 times the energy, because then we're back to the simple scale argument. Okay, that if I have a mass and I put it on a scale, that's 1 unit of energy. I get 1 unit of compression. I get the second unit of compression, exactly the same size compression in the spring, by adding the second mass. I can't have 4 units of energy in the spring because I only did 2 units of work to create that compression. So that sort of catastrophically fails. So the math makes it impossible. So I'm just saying that, okay, you can't do any conversion by paying attention to what the mathematical formulas produce as an outcome. There's just no way to make a conversion. But I would argue that when you do the other conversion, which is you take the explicit definition of what a joule is, and what a kilogram is, and what a newton is, you're stuck, because there's a direct relationship, and it's not consistent with this, of course. Alright, so let's move on to those numbers. Alright, I have returned. So when you do these dropping tests and create an impulse, it is what it is. It's a certain amount of impulse energy. You can measure it with a blob of clay, you can measure it with a spring, lots of ways to collect the energy. And it's an amount, and it can be defined pretty much as all momentum events anyway, as weights. It's a pressure applied, and it doesn't matter whether it's over time or not. It's a total amount that's either going into the object or it's going to reflect, and you'll see that. So it's either elastic or inelastic. It's either collected or it's reflected, but it's an amount. So anyway, so a newton is defined as 102 grams, I guess. Okay, so I don't know why it's not 100 grams, but it's the weight of that. And the argument is if you drop that, at least the 102 part, okay, instead of 100, 1 meter, that's a joule. So they use things like an apple, or they'll use a stick of butter, okay, because that's about 100 grams. And you drop it on 1 meter, and the impact is a kilogram. Now, I'd argue the impact is completely measurable on a spring, just like any other weight or impulse impression. And that impression is just like the newtons itself. I mean, it's no different than weighing the 100 grams and then having a deflection in the scale that reads 1 kilogram. Those things are comparable. So clearly by that definition, okay, 1 newton is 1/10, okay, of a kilogram, because it's 1/10 of the mass. It's 1/10 of the weight, and the weight is a measure of progressive capacities to apply pressure, and they're consistent by Hooke's law again. All right, so by that simple experiment, it's basically saying a newton is 1/10 of a kilogram, and it's pretty hard to sit there and argue with it. It's pretty direct. But then when you start analyzing the other definitions of how things move, it starts to get indirect. So you could argue that there's a certain velocity that the 100 newtons will have, or 1 kilogram will have, or 500 pounds will have. Doesn't matter. They'll have the same velocity dropping 1 meter. And that velocity is 4.4 meters per second. And so if you do that calculation, you end up with the momentum, okay, being 0.45. And you end up, so you have 0.45 equals 1 joule. So now the momentum is more powerful than the joules. So 1 newton, or 1 newton second, would equal 2 joules. So, it just doesn't make much sense, especially when you start considering the math equations and whatnot that are using these two terms in an equation. So, I just argue it doesn't make much sense. And so the simple truth is, though, is that that's how it turns out. A kilogram, the weight of a kilogram is a joule. So a kilogram just sitting on a table or something is applying a joule. And it's applying it because we can also tell if they do the experiment, this experiment right over here. I think you can see the mouse. Oh, this one. Yeah, sorry. This one right over here, where you just swing a kilogram into a scale. And the fact is, if you swing it with a velocity of, that would be the same as dropping it 1 centimeter, you'll end up with this 0.45 as your velocity. And if 1 kilogram at that velocity will be 1 joule. It'll weigh 1 kilogram. That's what the spring will say, is it's 1 kilogram. Just like if you had it this way sitting on the scale, it would be the same difference. So basically, dropping 1 centimeter adds a kilogram to the weight. So if you dropped 1 kilogram from 1 centimeter in gravity, it would weigh 2 kilograms because it's its weight plus the impulse energy you added to its weight. But if it was just thrown at a scale, not in gravity, 1 kilogram thrown at 0.44 meters per second, which is 1 mile an hour, would deflect the spring the same as 1 kilogram would in gravity. So those are pretty strong indications of the weight. So I guess this was just diagramming the fact that 1 kilogram on a scale is 1 joule. All right. I can't drop equals. I can't. I don't know what that says. That's funny. 1 centimeter drop, is 40.44 meters per second. So a full meter is 4.45. So that makes perfectly good sense with the 10 notion, that there's 10 units of this and 1 unit of that. So 1 centimeter drop is 1/10 of the impact energy of a full meter drop. And so it's 1/10 of the weight. And so, it perfectly matches the 4 times the distance thing. If you do the math, it works out perfectly that your weight doubles at 1 centimeter. At 4 centimeters, it doubles again. So if it was 1, it goes to 2, then it goes to 4, and then it goes to 8, and then it goes to 16. Just keeps going up. And in this case, we were talking about grams. So you'd go 100 grams with a 1 centimeter drop. Then the 4 centimeter drop would be 200 grams. And then the 16 centimeter drop would be 400 grams. And it just keeps going. And it works and it fits perfectly. So it makes a lot of sense to simply argue that, yes, this diagram by the geometry and recognizing that all of these things are impulse impacts. So when you say the train has 200 joules of energy and kinetic energy going down the track, how can it be any different when you're going to go collect it on a spring? You can't get 2 different spring compressions. because we know the momentum compresses the spring because all these experiments indicate that. And the kinetic energy can't also compress the spring. So that's the simplest argument, is what we need is all these tests done to prove that somehow twice the spring compression is somehow 4 times the kinetic energy, even though you can compress a spring twice with only 2 units of work. So that's the real test, and those tests we don't have done by any credible scientists. And even the momentum test of just starting to bang things into a scale turned horizontally, just to see what the impulse energy is, and see if it does hold consistent, that 1 centimeter will get you twice the weight, well, 1 unit of weight in the case of going horizontally, and that you'll double that at 4 centimeter drop, and that you'll quadruple that at a 16 centimeter drop. And the more you drop from the 4 times the height, you just keep doubling the weight. And that appears perfectly consistent with everything drawn here anyway. Alright, so that might be enough of a video just to make the point that by the functional results of experiments, you can convert newtons into joules. But clearly the fact that the v squared part of it just makes the kinetic energy number always irrational. So why would you bother? Because frankly, you're getting the accurate description by just saying how much does it weigh. How much does it weigh? When it hits something, you're just weighing it. The thing collecting the energy is just going to weigh it. And all you can do is understand that if some of the energy goes back this way, reflects, well, that isn't energy this way. So the scale's not going to read the rebound energy. It's just going to read the energy that goes in, not the energy that flies back out. Alright, that should be enough of a statement. I mean, this all goes back to the law of the lever. I mean, I can play Feynman talking about the lever and the clear proportions. Whatever the distance increases, that's going to end up being a velocity increase. That's how much you're going to be moving. Alright, so yeah, that's probably enough. Alright, so till the next time and such, and so forth and whatnot. So again, this is a response video basically to icansciencethat, who's just, substantially, completely cheating the rational argument that conservation of energy really does demand that you account for all the energy in a system. And these experiments done by physics don't do any of that, frankly. And so the next video I'll be doing in the series of videos challenging physics to explain, why you can't collect kinetic energy. That in every single case, you can't collect it. You can't make it do any work. All it always creates is heat. Lost energy, not successfully transferred energy. Alright, that's probably enough of a video. And so, till the next time and such. So anyway, so the icansciencethat guy, the real challenge was just such a simple experiment. Again, physics they won't give you the answer. They don't have the experiment in their file somewhere. And the simple argument is you roll something on a surface, all of its energy will be lost to the surface. And the simple contention is well, if you just measure that energy, measure the heat, you'll know exactly how much energy the object had. And physics just doesn't do the experiment. Obviously, their claim that something going 5 times as fast will put 25 times the heat into the ground, I would argue, is on its face silly. And they really have a responsibility to produce evidence if they're going to defend that statement. But they won't produce the evidence. Alright, enough of the video. Till next time and such.